In the spring of 1943, a woman sitting at a mechanical desk calculator in a converted lecture hall at the University of Pennsylvania was doing something that the United States Army needed desperately and could not get enough of fast enough. She was computing a single artillery trajectory, the curving path a shell would follow after leaving a particular gun, fired at a particular angle, under particular wind and temperature conditions, by hand, using a desk calculator and a set of differential equations, one arithmetic step at a time. A single trajectory took her most of a day. A complete firing table, covering the full range of angles and conditions a single gun might be used under, required several hundred trajectories. It took, on average, somewhere between 30 and 40 days of this work, performed by a room full of women hired for exactly this purpose, to produce one usable firing table for one gun. The Army had dozens of guns. It was introducing new ones constantly. The backlog of tables waiting to be computed grew faster than the women in that lecture hall, however quickly they worked, could ever clear it. Nobody at the Army's Ballistic Research Laboratory described this as a solvable problem in early 1943. It was simply the cost of artillery. Guns needed tables. Tables needed weeks of human arithmetic. This was the arrangement, and the only response anyone had to its inadequacy was to hire more women and build more desk calculators, which is exactly what the Army was doing, with diminishing returns, as the war demanded more guns, more shells, and more firing conditions than any reasonable number of human calculators could keep pace with. The mathematics itself was not the obstacle. The equations describing a shell's flight had been understood for decades. The obstacle was speed, the sheer number of repetitive arithmetic operations required, multiplied by the sheer number of tables the war demanded, multiplied by the brutal fact that a human being, even a very fast one, with a very good mechanical calculator, can only perform a few operations per second. A physicist at the University of Pennsylvania's Moore School of Electrical Engineering, teaching a wartime course to military officers, had a different idea, and he had been quietly nursing it for nearly 2 years before anyone, with the authority to fund it, took him seriously. John Maudsley was in his mid-30s in 1943, a mild-mannered, intensely curious man who had become fascinated, before the war, with vacuum tubes, the glass electronic components used at the time mainly to amplify radio signals, and with a question almost nobody in his field was asking seriously: could vacuum tubes, switching on and off thousands of times faster than any mechanical relay or gear, be used to build a calculating machine with no moving parts at all? The conventional engineering wisdom of 1943 had a clear and well-reasoned answer: probably not, and certainly not at any scale that mattered. The differential analyzers and relay-based calculators already in cautious use were built on mechanical or electromechanical principles, specifically because those principles were reliable. Vacuum tubes burned out. Everyone who had ever owned a radio knew this. A calculating machine built from a handful of tubes might work. A machine built from the thousands of tubes that any serious computation would require was widely assumed, by engineers who understood tube failure rates, to be a machine that would break down constantly and accomplish nothing useful between failures. Maudsley, together with a brilliant young engineer named J. Prosper Eckert, barely in his 20s, technically gifted enough that Maudsley had specifically sought him out as a collaborator, believed the conventional wisdom was solving the wrong problem. Yes, individual tubes failed. But if the failure rate of a single tube could be reduced, through careful engineering, to something low enough, then a machine built entirely from tubes could run at electronic speeds, thousands of times faster than any mechanical device, and simply outrun the problem that mechanical calculators could never escape. In April 1943, with the Ballistic Research Laboratory's backlog of firing tables now a serious operational concern, Maudsley and Eckert's proposal for an all-electronic calculating machine finally reached someone with the authority and the desperation to fund it. The machine they built over the following 2.5 years became known as ENIAC, the Electronic Numerical Integrator and Computer, and almost everything about it was a direct, physical consequence of the bet Maudsley and Eckert had made. To achieve the speed they wanted, ENIAC needed roughly 18,000 vacuum tubes, along with 70,000 resistors, 10,000 capacitors, and some 6,000 manual switches. These components, wired together across 40 separate panels arranged in a U around the room, filled a space of about 1,800 square feet, roughly the footprint of a large house, and weighed in at approximately 30 tons. The machine consumed about 150 kilowatts of electricity, an enormous draw for a single piece of equipment by the standards of the day. It was, by any ordinary measure, an enormous, room-devouring, electricity-hungry monster, built to solve a problem of pure mathematical speed, and constructed at a scale that nobody outside the project had previously associated with arithmetic. The tube failure problem that conventional wisdom had warned about did not disappear simply because Maudsley and Eckert believed it could be managed. It had to actually be managed, in practice, every single day. With 18,000 tubes operating continuously, simple statistics guaranteed that some of them would fail regularly, by some accounts, on the order of one tube every couple of days, sometimes more. Finding a single burned-out tube among 18,000 identical-looking components, each one buried inside a wall of panels, was its own engineering discipline. The team eventually discovered that running the tubes at voltages somewhat below their rated maximum dramatically extended their working lives, trading a small amount of performance for a large improvement in reliability. A fix that came not from theory, but from the team's own grinding, repetitive experience, keeping the machine alive. ENIAC's hardware, formidable as it was, solved only half the problem. A machine this complex needed to be told, in extraordinary detail, exactly what calculation to perform, and ENIAC had no software in the sense the word would later acquire. There was no keyboard, no stored program, no simple way to type in a new problem. ENIAC was programmed by physically rewiring it, plugging patch cables between panels, setting thousands of mechanical switches by hand, in a configuration that mirrored the exact sequence of mathematical operations a particular trajectory calculation required. Reprogramming the machine for a new kind of problem could take days of physical labor before a single calculation began. The people who learned to do this, who turned a room of vacuum tubes and switches into a working calculator for a specific equation, were 6 women hired originally as part of the Army's existing core of human computers. Kay McNulty, Jean Bartik, Betty Holberton, Marlon Meltzer, Frances Spence, and Ruth Tatelbaum. They were given the machine's circuit diagrams, with essentially no formal instruction in how an electronic digital computer worked, because nobody else fully understood that yet either, and were expected to work out, largely on their own, how to translate a firing table calculation into a physical wiring configuration. They succeeded, and the success required a kind of technical judgment, reading the machine's logic directly from its physical wiring, predicting how a change in one panel would ripple through the rest of the calculation, that few people inside or outside the project at the time fully recognized as the sophisticated engineering work it actually was. For decades after the war, public accounts of ENIAC's unveiling tended to feature the machine and its male designers prominently, while photographs of the women who had programmed it were, for years, captioned as anonymous models, posed beside the equipment rather than identified as the engineers who had made it run. ENIAC was completed in February 1946. The war it had been built to help win had ended 6 months earlier. This is the structural irony sitting at the center of the entire project. The ballistic research laboratory's desperate backlog of firing tables, the urgency that had unlocked the funding, and the wartime priority access to scarce components, the entire justification for building a 30-ton electronic monster. All of it had been resolved by Japan's surrender before the machine built to resolve it had finished being built. ENIAC did not sit idle, and its first major task after completion was, fittingly, not an artillery table at all, but a set of calculations supporting the design of the hydrogen bomb, run for the weapons laboratory at Los Alamos in late 1945 and into 1946, a sign of how quickly the machine's usefulness had outgrown the narrow military problem it had originally been built to solve. It went on to perform genuinely useful scientific computation for nearly a decade, demonstrating, far more persuasively than any sales pitch could have, that the all-electronic approach Mauchly and Eckert had bet on actually worked. But the machine's own limitations remained severe. It could store almost no data internally. Reprogramming it remained a multi-day physical undertaking. Its public unveiling in February 1946 generated press coverage describing it, with considerable enthusiasm, as an electronic brain. Coverage that overstated what the machine could actually do on its own and understated how much human labor, much of it performed by the uncredited women who ran it, was required to make it do anything at all. ENIAC's troubles did not end with the war it missed. A quieter crisis was waiting decades later in a courtroom. Mauchly and Eckert had left the University of Pennsylvania shortly after the war to commercialize their invention, and they spent years pursuing a patent on the electronic digital computer itself. A patent that, if it held, would have entitled them to royalties on essentially every electronic computer built afterward. The patent was finally granted in 1964, by which point Eckert and Mauchly's company had been absorbed into Sperry Rand, and Sperry Rand began collecting licensing fees from other computer manufacturers on the strength of it. In 1973, after a lawsuit brought by Honeywell, a federal judge in Minnesota invalidated the ENIAC patent entirely. The ruling found that Mauchly had visited a physicist named John Atanasoff at Iowa State College in 1941, had seen and discussed Atanasoff's own earlier electronic calculating machine, a device called the Atanasoff-Berry computer, never patented and never built into anything resembling a finished product, and had derived key elements of ENIAC's design from that visit without sufficient originality to deserve a patent of his own. 3 decades after the machine had been built, the very question of who had actually invented the electronic digital computer was reopened, argued in court, and decided against the men who had spent 30 years receiving the credit. The final irony belongs to the numbers themselves, and it is the reason this particular machine has remained, for 80 years, the standard example anyone reaches for when they want to illustrate how far computing has come. ENIAC, in full operation, could perform approximately 5,000 additions per second. A smartphone sitting in an ordinary pocket today performs billions of operations per second, a difference measured not in multiples, but in orders of magnitude, achieved by a device that weighs a few ounces, fits in a hand, and runs for a day on a battery smaller than a deck of cards. The 30-ton, house-sized, power-hungry monster that 6 women had to physically rewire for days just to change which equation it solved has been outperformed, by a margin that borders on the absurd, by a piece of glass and silicon that most people replace every few years without much thought. This is not simply a story about a machine becoming obsolete. Every machine becomes obsolete. It is a story about the price of a beginning, about how much room, how much electricity, how much physical wiring, and how much uncredited human ingenuity it took to prove, for the very first time, that an entirely electronic machine could calculate fast enough to be worth the gamble. Everything that came afterward, every transistor radio, every mainframe, every laptop, every phone now outperforming a 30-ton ancestor by a factor of millions, inherited its basic premise from a converted lecture hall in Philadelphia, where a room full of vacuum tubes proved, just barely and just in time to matter, for almost nothing it was actually built for, that speed could be bought with electronics instead of gears. A fragment of the original ENIAC, a handful of its panels, dark now, the tubes long since removed or burned out for good, sits today in the Smithsonian's collections, a small piece of a machine that once filled a room, kept beside artifacts of devices that now fit, with room to spare, inside a shirt pocket.